This is the third lesson about interpreting mass spectra. In this video, we'll determine a structure from an example spectrum. Here is a real mass spectrum. We'll assume that the molecular ion is in the high mass cluster. I've included a table of the intensity data for this group of peaks. Let's assume that the molecular ion appears at mass 116. There doesn't appear to be any bromine or chlorine or other important A+2 elements. And an even mass for the molecular ion suggests an even number of nitrogens. Let's calculate the carbon number. It's a little ambiguous, but the most likely number is 6. So what mass do we have yet to account for? 44 atomic mass units is much too much for this to be just hydrogen atoms. Let's consider 2 nitrogen atoms. That leaves 16 atomic mass units, which appears to be a reasonable number for hydrogen atoms in this molecule. So we have a formula of C6H16 and 2. Let's see if we get a reasonable number for the double bond equivalents, or rings plus double bonds. Well, it turns out we get 0. That's a reasonable number. It means that we have an entirely saturated molecule. We must have some sort of saturated amine. If we look at characteristics for amines, we see that they generally exhibit alpha cleavage at the radical site. We also observe that primary amines exhibit a peak at 30 atomic mass units. How does that happen? If we ionize by removing an electron in a lone pair associated with one of the nitrogen atoms, the free radical tries to form a new bond with an atom adjacent to it. That breaks a bond on the other side, and the charge remains on the nitrogen atom. We get a fragment at 30 atomic mass unit. This is usually a very strong peak, often the base peak for the primary amine. We do see a small signal. The fact that it is so weak suggests that we do not have a primary amine. What structures can we draw that meet these criteria? Here are a few. Let's look at a fragmentation data to see if there's any evidence that would support or rule out any of these structures. Let's start at the high mass end of the spectrum. Prominent peaks at the high mass end are very important and can be easier to explain with simple fragmentation pathways than at the low masses. For example, this peak at 101 is 15 mass units smaller than the molecular ion. It almost certainly represents the loss of a methyl radical. So, which of these molecules will lose a neutral methyl group easily? Let's consider the first structure. If we ionize the nitrogen atom on the right, then the radical will try to form a new bond with an adjacent atom, and we break off a neutral methyl radical. Notice that we needed to have an ethyl group attached to the nitrogen for this to work out. Structure 4 does not meet this criterion, so we can roll it out. The peak at 88 atomic mass units is very strong. It represents the loss of 28 from the molecular ion. The only way that we could do that with a combination of atoms that are in this formula is by losing ethylene or a molecular nitrogen molecule. Losing N2 might be tricky since these atoms are not adjacent to each other in any of our structures. Even if they were adjacent, as in a hydrazine molecule, we would need to break at least 4 bonds in order to lose molecular nitrogen. It is possible to lose a methylene molecule. Using structure 1 again, we consider ionizing the nitrogen on the right, and it's common to have a hydrogen atom migrate to a saturated heteroatom. Unlike for a McLafferty rearrangement, we do not need a 6-member transition state for this mechanism to occur. Once the hydrogen moves to the nitrogen atom, the radical will try to form a new bond. A molecule of ethylene is released in the process. Once again, structures with an ethyl group attached to a nitrogen will lead to a loss of 28. Let's look at the tallest peak in the spectrum. It appears at a mass-to-charge ratio of 71. So it represents a loss of 45 atomic mass units from the molecular ion. How can we lose 45 atomic mass units from this formula? For a molecule this small, you can quickly come up with combinations on your own. However, there are some handy tools on the internet for calculating the elemental composition associated with a given mass. Worth a try. The only combination of atoms that could be a subset of this formula that give a mass of 45 is C2H7N. So if we lose that fragment, the charge remains on the other piece, which would have a formula of C4H9N. If we calculate the number of double bond equivalents associated with that formula, we get an integer. An ion with an integral value of number of rings plus double bonds must also be an odd electron ion. Therefore, the piece that was lost as a neutral must have an even number of electrons. That implies that the loss was a neutral molecule. Either ethylamine or dimethylamine must have been lost. How might that happen with our candidate structures? Consider ionizing the nitrogen on the left. If a hydrogen atom migrates to the nitrogen, we might lose dimethylamine by inductive cleavage. That would give us a charged fragment of 71 atomic mass units. However, the literature shows that when the charged site appears on a nitrogen atom, then the most likely process to follow a hydrogen migration would be an alpha cleavage initiated at the radical site. Although this pathway leads to the proper fragment, it's not very likely for amines to do this. Certainly, the probability is not great enough to expect it to lead to the base peak in our spectrum. Every one of our candidate structures, and all of those that I've neglected to draw, such as hydrazines, have the same problem. They can't explain the prominent peak at mass 71. So let's reconsider our elemental composition. Let's try 2 oxygen atoms. That would leave 12 atomic mass units, or 12 hydrogen atoms. From our new chemical formula, we would calculate 1 double bond equivalent. Let's think about functional groups. Before we draw candidate structures, consider whether there are some prominent features that might be missing in the spectrum for any of these groups. For example, carboxylic acids tend to lose a hydroxyl radical, which means a loss of 17. A loss of 17 from a molecular weight of 116 gives us a mass of 99. But there is virtually no signal at 99, so we can rule out carboxylic acids. Aldehydes tend to show very strong loss of a hydrogen radical. But there's only a very tiny signal at 115. An aldehyde is an unlikely candidate. Primary alcohols are prone to losing water. Likewise, there is very little or no signal at 98 atomic mass units that corresponds to the loss of water. It's very unlikely that our unknown is a primary alcohol. This leaves us several combinations for 2 oxygen atoms and a ring or a double bond. Here are a few candidates for esters and some others that are ketones. Here are some alkene candidates. And here are a few ring-containing candidates. There are many more examples with different branching arrangements that we could draw. However, if we work through these candidates, then it will become clear what structural features work and what does not. Recall that this molecule should exhibit the loss of a methyl radical. Let's see how this might happen with a few of these structures. Let's consider structure 2. If we ionize at the saturated oxygen, then alpha cleavage leads to the loss of a neutral methyl group. Most of the candidates that I've drawn here can lose a methyl group. In order to save time, I did not bother drawing structures that would not cleave off a neutral methyl group. Let's consider what a radical site-initiated cleavage mechanism will do in the case of structure 3. If we ionize at the saturated oxygen atom, then the most likely bond to break will result in losing an ethyl radical. Do we see a peak at 29 atomic mass units below the molecular ion at a mass of 87? No, there's nothing there. So we can rule out structure 3 and many others that we would expect to lose an ethyl group. We can see that there are many alkene structures that we would expect to lose a neutral ethyl group as well. With an alkene, ionization can occur at the double bond as well. Subsequent alpha cleavage can also produce ethyl radicals. In a similar manner, we can predict the loss of an ethyl radical from two of these ring structures. Peak at mass 88 is very important because of its intensity, but also because it appears at an even mass. Recall that a molecule with an even mass produces odd electron ions with even masses also. Here we have a loss of 28 that could only be explained by losing either an ethylene molecule or carbon monoxide. Which structures might produce a loss of 28? Let's consider this ester again. When the carbonyl is ionized, it can form a six-member transition state and follow a McLafferty rearrangement. Ethylene is lost as the neutral product. Structure number 4 can also lose ethylene, but by a different pathway. If the saturated oxygen ionizes, a hydrogen atom moving from the terminal carbon leaves behind a radical site that can cleave an ethylene molecule off the far end. Similar mechanisms can be written for all but these two ketones. Several of these alkene structures can be eliminated because they will not show a loss of 28. Likewise, many of these ring structures produce odd electron ions, but none with the accompanying loss of 28. Recall that the base peak at 71 atomic mass units corresponds to a loss of 45. The high intensity indicates that this is a very easy and very probable pathway. The possible fragments will have to be one of these two elemental compositions. Let's look at structure 2 again. If we ionize at the carbonyl oxygen, we can have a radical site-initiated cleavage, giving rise to the loss of C2H5O. The charge remains on the fragment that weighs 71 atomic mass units. We might also imagine a net loss of 45 through another pathway. We have seen this structure lose an ethylene molecule. An induction step might move the positive charge to the carbon atom. Now, a radical-initiated cleavage would remove a neutral hydroxyl radical. The result would also be an ion at 71 atomic mass units. Each of these esters and two of the ketones can follow similar pathways to produce a charge fragment at 71. The other candidates cannot. Among the alkenes, structure 17 and 35 can also be eliminated for the same reason. Several of the 5-member ring compounds also do not lead to a peak at 71. Notice that although it is eclipsed by the much taller peak at 71, we see an important ion at 73 atomic mass units. The loss of 43 suggests a propyl radical, or one of these species with a double bond. We can see that structure number 2 will cleave a propyl group easily. So any molecule with a structure given here can give rise to a signal at 73 atomic mass units. So structure number 10 will follow a similar path. Likewise, 4 carbons attached to a saturated oxygen atom will lose a propyl group. This carbonyl and its neighboring methyl group may be lost by an inductive pathway. However, none of the remaining ring structures will exhibit either type of mechanism. They can be ruled out. Let's look at the alkenes. An oxygen atom next to a terminal alkene can also be lost through an inductive mechanism. So this group will give us the fragment that we want. But neither structure 28 nor 32 can lose a neutral fragment of 43 easily. So here's what's left. How can we distinguish among the 6 remaining candidates? Note that there's a significant peak at 89. It is true that whatever fragment appears at 88 might be expected to have a heavy isotope version, giving rise to some signal at 89. However, this is much too tall to be explained easily that way. The loss of 27 from our molecular formula can only be explained by the loss of a neutral fragment with composition of C2H3. Several of the remaining candidates are esters. That functional group is prone to a hydrogen rearrangement mechanism known as a McLafferty+1 mechanism. The process starts out in the same way as a McLafferty rearrangement. A hydrogen atom is transferred, followed by a pair of electrons moving out of the double bond to the oxygen atom. This transfers the charge to the carbonyl carbon. Now the radical initiates the formation of a double bond, but before the neutral alkene can move away, the free radical, now on the oxygen atom, snatches the hydrogen atom from the alkene. The result is a charged fragment with 2 alcohol groups and a mass of 89. Although a similar process is common to each of the esters, none of the remaining structures will lose C3H5. Structure 2 is the only candidate that fits all of the criteria. Indeed, we've been looking at the spectrum of ethyl butyrate.